A mode 16 counter uses 4 JK flip-flops as diagrammed here. In this circuit, the output at Q becomes the clock input for the next JK flip-flop. Each JK flip-flop is open, thus they are set automatically to high or 1, which keeps them in their toggle position. The counter starts at 0, 0, 0, 0. As pulse 1 arrives at the clock input at flip-flop 1, it toggles on the negative edge. The output at Q1 will go from low to high, or 1. Thus, the counter will be at 0, 0, 0, 1. When clock pulse 2 arrives at flip-flop 1, it returns output Q1 back to 0, which causes flip-flop 2 to toggle to 1. The output at Q2 is 1, and the count on the display now reads 0010. The counting continues, with each flip-flop output triggering the next flip-flop on its negative going pulse. The 1's position, or A, must change its state on every count. Thus, flip-flop 1 must toggle for each clock pulse. The 2's position will change its state half as often as the 1's position. Thus, flip-flop 2 will only toggle half as much as flip-flop 1. The 4's position will change less often than the 2's position, and the 8's position less often than the 4's. Thus, each more significant bit will toggle fewer times. Let's observe how a sequence of 10 clock pulses will ripple through a series of 4 flip-flops in this 4-bit counter. As we have shown, the first clock pulse generates a binary output of 0001, and the second, an output of 0010. As the remaining pulses arrive at the input, the third pulse toggles Q1 back to 1, with Q2, Q3, and Q4 remaining unchanged, and the output is 0011. Pulse 4 again toggles Q1 back to 0, with Q2 toggling to 0 and Q3 to 1, with Q4 unchanged, and the output is 0100. These toggling patterns, triggered on the negative edge of the clock pulse, continue, with pulse 5 giving an output of 0101. Pulse 6 outputs 0110. Pulse 7 outputs 0111. The 8th pulse results in an output of 1000. Pulse 9 a 1001. And finally, as expected, the 10th pulse toggles the appropriate flip-flops to give 1010.